The topic is NP hard and NP complete. This is the most important topic and also this is the most confusing topic. But I guarantee that I'll make these concepts very much clear for you. And one more thing, don't watch this video if you are in a hurry. Watch it when you are really prepared to watch this one, when you are ready to watch this one. Okay, let us start what this problem is. See, actually this topic is a research topic. This is related to research. So what is there for doing research here? First, let us know about that. See, all the algorithms that we know or already we have learned, I have written them here. These are the algorithms which takes polynomial time, and these are the algorithms which takes exponential time. The problems for which we know the algorithms which take polynomial time. Like searching algorithm, the problem is searching and the algorithms are linear search, binary search. This takes n time and this is log n time, and this is n square for sorting, and merge sort is faster than that, that is n log n. Likewise, zero knapsack problem which takes 2 power n time, and traveling salesperson 2 power n. All these are exponential. They may be taking n into 2 power n, or some is n power n, some are, but I just wrote them as 2 power n in common to show that those are exponential. Now here we have categorized the algorithms into two. One is polynomial time taking algorithms and exponential time taking algorithms. What is the scope for doing research here? Let us see. See, for searching we have a linear search algorithm which takes order of n time, and faster than that is binary search which takes log n time. We are in search of algorithm which is much faster than this one, that is order of 1 time. We want some searching algorithm which takes order of 1 time. Similarly, the fastest sorting algorithm takes order of n log n time, and one of the sorting is merge sort. We want faster sorting algorithm that should take order of n time faster than this one. Similarly, for these exponential time algorithms, we want polynomial time algorithms. All these problems which are taking exponential time, we want faster and easy method to solve them in just polynomial time, because 2 power n or n power n or 5 power n, anything is much bigger than polynomial time. Even n power 10 is smaller than 2 power n for some large values of n. Even n power 100 is also smaller than 2 power n for some very large values of n. So these are very time consuming algorithms. So we want polynomial time algorithm for them. This is the requirement. And even for this also we want faster algorithms. This is the requirement. Now this is a research area. The person from computer sciences or from mathematics can solve these problems. So people have been doing research on this one. But there is no solutions found so far yet for solving these problems in polynomial time. Then when the research work is going fruitless, right, we want something such that whatever the work we done should be useful. So there are guidelines, or we can say framework made for doing research on these type of problems, that is exponential time problem. And that framework is NP hard and NP complete, or guidelines, that is a part of framework is NP hard and NP complete. So let us see what is the basic idea behind that. So there are 2 points that I am going to tell you. Based on this, the entire topic is based on these 2 points only. I'll discuss them in very much detail, but just I am telling you those 2 points, right? See, first point. When you are unable to solve these problems, when you are unable to get a solution, that is polynomial time algorithm for them, then at least you do the work such that you try to show the similarities between them, so that if one problem is solved, all other problems should also be solved. We will not be doing research work individually on each and every problem. Like I am trying to solve knapsack problem and you are working on graph coloring. We will not do it individually. Let us combine them collectively and put some effort such that if one problem is solved, all the problems should be solved. So for that, we have to show the relationship between them, association between them, to show that the properties they are having are similar, so that if one is solved, the other can also be solved. This is the first objective, that try to relate the problem, either solve it or at least relate it. This is first one. Second thing is, when you are unable to write algorithms for them, that is deterministic, why don't you write non-deterministic algorithms for them? When you are unable to write polynomial time deterministic algorithm, why don't you write polynomial time non-deterministic algorithms? So what are these? Let us see. So these are the 2 points I have shown you. Now I'll start with non-deterministic algorithms. Then I'll go to the relationship between them. Once we understand these 2 things, everything is clear. Let us check. Let us talk about non-deterministic. See, the algorithms that we write usually are deterministic. So what does it mean? Each and every statement, how it works, we know it clearly. We write the statements, we are sure how they work. So we know the working of the algorithm. So that is a deterministic. So we can write non-deterministic algorithm also. Yes. That means we don't know how they are working. So how we can write algorithm which we don't know? See, if I am trying to write a 0-1 knapsack problem, that is polynomial time algorithm, if I am trying to write, then I may be knowing most of the statements, but some of the statements that I may not be figuring out how to make them polynomial. So leave them blanks and say this is non-deterministic. So when I come to know that how it has to be filled, I will fill up that statements. So in a non-deterministic algorithm also, most of the statement may be deterministic, but some of the statements are not deterministic. So in this way, what we can do is by writing non-deterministic algorithm, we can preserve our research work so that in future somebody else is working on this same problem, he can make that non-deterministic part as deterministic. This is the idea. So suppose I have spent 10-12 years to solve this one of the type of problem, but I was unable to solve. Then what all the work that I have done should be preserved in some form. So that is the idea behind writing non-deterministic algorithm. So how do we write non-deterministic algorithm? So here is an example for non-deterministic search algorithm. Now I'll show you what are non-deterministic statements in this one. This choice is non-deterministic, success and failure. These are the known statements that we use for writing non-deterministic algorithm. So these statements are non-deterministic. And we assume that all these statements takes just 1 unit of time. We assume that these are not taking order of 1 time. Now let me explain you the algorithm. This is for searching a key from an array of size n. Let us check. See, if I just simply look at this algorithm without going into detail, simply just see the statements, it seems that the entire algorithm takes order of 1 time. Yes, this is the constant time algorithm for searching. See, the fastest search method we know is binary search, which takes log n, but this algorithm is taking order of 1, so really it is faster. We need this one, but this is non-deterministic. Let us see how this is working. I'll explain. From an array, we have to search for key. So the first statement is what? Choice j. So choice is called and it has given index j. And what we do, it is giving us the index of that key element. It is saying that that key element is so and so position j. And we are checking is that key element is present at j. If so, then search is successful. We'll write the output and search is successful. If the key element is not there at that place, means key element is not present in an array. Means search is unsuccessful. So we say fail. Means solution is not there. Means key is not found. It's not that it's unable to find. It is able to find, but the key is not present in an array. So simple. Now the question is how this choice came to know that the key element is present at jth index. That's what it is non-deterministic. Once we come to know that we can find out the position of a key element in constant time, then we'll fill up this line. This is like a blank statement for us now. Once we fill up this, we have an algorithm which is taking order of 1 time. This is how the algorithm, non-deterministic algorithm should look like. Let's see how this choice is working. Suppose I have an array of elements. If I say key is 9 and search, then choice will give me directly index 4. How? I don't know. Without checking anything, without applying any search logic, directly it says at index 4 in constant time. And how it can know that in constant time, today we don't know. Maybe tomorrow we can find out a method to directly get that answer. That is the idea behind writing non-deterministic algorithm today. Tomorrow they may become deterministic by some other researcher. I am unable to do it, maybe other person will be able to do. My work is preserved. This is the idea behind it. See, one more thing I will say, that how this choice is working, we don't know. When we don't know how the things are working, we call it as magic. So this is magical now for us. Once we know how it is working, it becomes a technique. Right? It becomes a logic. So same way, today it's a magic for us. So we have written like a magical algorithm. Tomorrow it will be procedural, or it will be having its own logic. So once we know that, it becomes a deterministic and it will be taking constant time. So like this, we can write down non-deterministic algorithm for these polynomial time, exponential time taking algorithms. That is, we will write on polynomial time algorithms. This is polynomial time. We'll not write exponential again, it's waste. We will be writing non-deterministic, which is taking polynomial time for these type of problems, which are right now taking exponential time. So with this, we define two classes here. Let us see. We define P. P is a set of those deterministic algorithms which are taking polynomial time. Example, linear search, binary search, bubble sort, merge sort, single source shortest path, minimum cost spanning tree, optimal merge pattern, Huffman coding, all these takes polynomial time. So all those algorithms which takes polynomial time and the algorithms are deterministic, we call them as P. And we have one more class of algorithm, that is NP. These algorithms are non-deterministic, but they take polynomial time. For whom we will try to write? We try to write for these type of problems. These are exponential, we convert them into polynomial, but we don't know how it is possible, so we leave the statements non-deterministic, so algorithm becomes non-deterministic. So non-deterministic polynomial time taking algorithms. So deterministic polynomial time taking algorithm and non-deterministic polynomial time taking algorithms. So P and NP. This is a famous diagram. This is NP and this is P. P is shown as subset of NP. What does it mean? The deterministic algorithms that we know today were the part of non-deterministic algorithm. Let us say merge sort, for example, we have found it recently. In the past, we were not knowing it. So it was non-deterministic for us. We were not knowing that there is a possible algorithm which takes n log n time. We were working with bubble sort maybe. So that was taking n square time, but recently we found out that merge sort, which is faster, is taking n log n time. So that algorithm was non-deterministic and became deterministic now. So this is the idea here. So whatever the research work we do and we come up with some new algorithm, we say that when we came to know the algorithm, that became deterministic. So it means it was already there and that was non-deterministic for us. Right? This is the idea set behind this one, that is P and NP. So today what all we know which are deterministic, where yesterday they were non-deterministic, and today whichever is non-deterministic, tomorrow that may become deterministic. So we say that deterministic is a subset of non-deterministic. And there is one more Cook's theorem here that try to prove that P is a subset of NP or P equal to NP, that I will come to it. So for the guidelines of research work or the framework for research work, I said that there are two things that are important. So first thing I have completed, that is writing non-deterministic polynomial time algorithms. How to write and what is the meaning, I have explained that. One part I have finished. Now the second part, I said that if you are unable to solve, at least show the relationship between them such that if one problem is solved, it should be easy for solving other problems also in polynomial time. We will not work on each and every problem individually. So how to relate them together, that is the next thing we will learn. So for relating them together, we need some problem as a base problem. So which problem we take it as a base problem? The base problem is satisfiability problem. What is this? This is a CNF formula, that is propositional calculus formula, using Boolean variables. Let us say x1, x2, x3. I have three Boolean variables like xi are these. Then There is a formula, that is CNF formula is there. Example formula I am taking, that is x1 or x2 bar or x3 and x1 bar or x2 or x3 bar. Let us take this as an example formula. This is CNF propositional calculus formula and it is having clauses, let us say C1 and C2. These are the clauses and clauses are formed using disjunction and they are joined with conjunction. So this is CNF formula. Now what is this satisfiability problem? The satisfiability problem is to find out for what values of xi this formula is true. So what are the possible values of xi? See, x1, x2, x3, as these are boolean, so they can be 0 or 1, so they can all be 0 or this can be 1 or this can be 1 or these two are 1, 0 0, 1 0 1, 1 1 0, 1 1 1. So there are 8 possibilities. I should try all these 8 possibilities and place them here and check for which of these values this is true, and I should find out all possible values for which it is true. So how much time it will take for solving this one? So how many values I should try? 8. 8 is what? 2 power 3. So for n variables it will be 2 power n. So this is also exponential time taking problem. This is 2 power n, that is exponential time. So this is similar to this. They are also taking 2 power n or exponential. So this is also taking exponential time. So this belongs to the same category. Now these values, even I can show them in the form of a state space tree. I will prepare a state space tree for this. The solution for this problem, I can say that x1 is 1 or x1 is 0 or x2 is 1 or x2 is 0 or x2 is 1 or x2 is 0. There are 3 variables, so x3 it can be 1 or 0, 1 or 0, 1 or 0, 1 or 0. Now the path from root to the leaf of these tree gives a solution like 1 0 1, this one. If I take this, this is 0 1 1. So this is showing all 8 possible values of x1 xi, x1 to x3. So this is represented in the form of a state space tree. So this problem can also be represented in the form of a state space tree. Now what we have to do? We have to show that these are similar to this one, such that if satisfiability is solved in polynomial time, all can be solved in polynomial time. Or any one of them is solved, then all of them can be solved in polynomial time. So this is the idea. We have to relate these problems so that we don't have to solve them individually. If one is solved, all are solved. Now how to prove that? There are different methods for showing that. But to make it simple and understand, I'll show you here only by taking 0-1 knapsack problem by using this tree. Let me take an example of 0-1 knapsack problem. Here I have an example of 0-1 knapsack problem. There are 3 objects given. For each object there is some profit and there is some weight and the capacity of the bag is 8. We have to fill up the bag such that the profit is maximized and we should not exceed the capacity of the bag. Then to give the solution for the 0-1 knapsack problem, I can write down solution in the form of xi, that is first value or second and third value can be either 0 or 1 or 0 or 1 or 0 or 1. Means all these values x1, x2 and x3 can be either 0, 0, 0 or 0, 0, 1 or 0, 1, 0. So how many possibilities are there? 2 power 3. So it means for n objects it will be 2 power n. So the solutions that are required for this one are similar to satisfiability problem. How we solve satisfiability? Same way we have to try for 0-1 knapsack. There we have to see formula is true or not. Here we have to see whether the profit is maximized or not. So it means this problem can also be solved using state space tree. Already you can check some video for 0-1 knapsack problem. I have drawn a state space tree. So I will show one thing now. I have removed both the problem. There is no satisfiability formula. There is no 0-1 knapsack problem here. Now can you tell me this tree belongs to whom? This tree is showing the solutions for satisfiability or 0-1. This is for both. So this is how I am relating them, right? There is a different method for relating, okay, that we will learn in next video. You can watch it, but here I am relating like this. So you can clearly see that if you can solve this state space tree in polynomial time, then means you can get the solution for this one also in polynomial and this one also in polynomial. So that's how we show the relationship between these problems by taking this as a base problem. Now I will add this one also there in the list. Satisfiability I also have included in this exponential time algorithms. Now we coin one term, that is NP hard. What is this? I'll explain, but let us call them simply as hard problem. All these are hard problems, right? First of all, let me call it as hard. But satisfiability, as we have taken it as a base problem, so I'll say that is NP hard. What is NP? I'll explain afterwards. Let us simply call it, this is NP hard. And this all I am saying hard problems. They are taking exponential time. They are not NP hard. Then I was saying that we have to show that these are related to satisfiability only, so that if that is solved, all can be solved. Now how to show the relationship is, the procedure is reduction. So what this reduction is? We take, let us say example, satisfiability problem, and we take one of the problem, for example 0-1 knapsack problem, and we say that satisfiably reduces to 0-1 knapsack problem. What does it mean? What we show? We show that we take some instance of satisfiability, that is one formula we take, and that formula, from that formula will convert into a 0-1 knapsack problem. We take an example of satisfiability problem and we convert that problem into 0-1 knapsack problem. And we say that if this 0-1 knapsack problem can be solved in polynomial time, and that same algorithm can be used for solving this also in polynomial time. So that's how it means, if this is solved, that can be solved. If that is solved, this can be solved. If some algorithm is solving this one in polynomial time, then same algorithm can solve this one also in polynomial time. Now who is solved first, that is a different thing, but this is how we show that they are related to one another. Any one you solve, all the other one will also be automatically solved. So how we show the relationship? We take an example formula and that formula will convert into 0-1 knapsack problem. And this conversion, for conversion we will not take much time, we take polynomial time only. We take polynomial time, we don't take exponential. Conversion itself is taking exponential time, then it's of no use. So conversion will be done in polynomial time. This is one important thing. Next, I said that this is NP hard. Let us call it as NP hard. Satisfiability is NP hard. This is NP hard, right? If satisfiability is reducing to 0-1 knapsack problem, then this also becomes NP hard. Now this problem comes into the class of NP hard. This means that if you solve any one, the other one automatically gets solved. So means we have proved the relationship between them. So if you are showing that satisfiably reduces to some problem L, then if it is proved, then this also becomes NP hard. This also becomes NP hard. And one more thing, this reduction has a transitive property. If satisfiability is reducing to L1, then L1 is also NP hard. And if L1 is reducing to L2, then L2 also becomes NP hard. Means if I have shown 0-1 is reduced by satisfiability, then I can show graph coloring reduced by 0-1, or some of the subset reduced by graph coloring, or Hamiltonian is reduced by graph coloring. I can show it like this. So you don't have to bring all of them onto satisfiability only. You can show others any one of the problem related to that, right? Either satisfiability or 0-1. So this is NP hard. If satisfiably reduces to any problem, that problem also becomes NP hard. Now one more important thing, satisfiability, if it is reducing to some problem, then that problem is also becoming NP hard. So this is one thing that is showing relationship. And one more thing we were doing, that we were writing non-deterministic algorithms. So do we have a non-deterministic algorithm for any of these problem? Yes, one of the problem that is we know, it is proved, it is there, that is satisfiability problem. For this we have a non-deterministic polynomial time algorithm. It's existing. So satisfiability is NP hard as well as this is NP complete. It's NP complete. If a problem is having non-deterministic time algorithm, then that problem also becomes NP complete. So satisfiability is a known NP complete problem. So for any of these problems, if this problem is reduced by satisfiability, so this is NP hard. This is NP hard. And if you write a non-deterministic polynomial time for algorithm for this one, then this also becomes NP complete. NP complete. So for doing research work on any problem of your problem, then you have to do two things. One, you have to show that this is directly or indirectly related to satisfiability, and you should write a non-deterministic algorithm for your problem. If you complete the first part, that is shown that it is reduced by satisfiability, then your problem became a part of NP hard class. And if you have also written a non-deterministic algorithm, then your problem has reached in a class called NP complete. Means you have completed the research work, basic required research work. If you are able to directly solve that problem, okay, solve it, whether good, well and good. If not, at least you should do this, then your research work is completed. Now I will draw one more well-known diagram. This is a set of NP hard problems. Who is there in this one? Satisfiability. Then, if you prove any of these problems that is reduced by satisfiability, let us say 0, 1, it also becomes a NP hard. If you prove graph coloring, then that is also NP hard. If you are proving that they are directly or indirectly reduced by satisfiability, they will become NP hard. They are coming into NP hard. This is one part we have to do as a part of research. Then the second part, we should also write non-deterministic algorithm, NP. This is another thing, writing non-deterministic algorithm. Do you have a non-deterministic algorithm for satisfiability? Yes. So this is in NP hard only, but this is in this intersection area. So this is also NP hard as well as this is having non-deterministic polynomial time algorithm. So what is this area called as? This is NP complete. This is NP complete. Intersection of NP hard and non-deterministic algorithms. That's all. The major part we have completed. Then one more thing we have drawn already, that is P was also there. This was another discussion we did, that P is the things that we are deterministic today and NP is that is non-deterministic, and tomorrow we may be knowing those non-deterministics also that will be coming inside P, and we believe that this P will be keep on expanding, right? This will be keep on growing, the P will become bigger and bigger, so that non-deterministic will be becoming deterministic, right? So we believe like this. Our circle of knowledge will be going on growing. That's how we believe. Now how much it is we don't know, so it will be going on growing, and we believe that at some stage it will go and become equal to NP. Means everything that is not known, we will be knowing it, right? That is the idea. One major problem remaining. The thought that we have that today we are writing non-deterministic, believing that tomorrow that will become deterministic. Is it perfect? Do you think it's really going to work? If it fails, we never found out that, then all our research work is waste. So for that, we need to prove that really tomorrow we may be knowing non-deterministic algorithm and they will be converted into polynomial time deterministic algorithms, right? So we have to at least prove that yes, what we are doing is right. So for that, if we are able to prove that P is equals to NP, we are able to prove that P is equal to NP, then it is proved that whatever the non-deterministic we are writing, tomorrow that may become deterministic. So for that, we say that P is a subset of NP. We don't know how much this is, so that's why we write equal also. Then we have to prove P is equals to NP, whether P is equal to NP or not. See, if you are proving P is equal to NP means it's existing, but you don't know. Right? It is existing. You don't have to do research and find out or invent it. It's existing. Discover it. So when you say P is equals to NP, so what is non-deterministic for you? It's existing. Just you discover it. That is the meaning. So if you are able to prove this, then what all the work that we are doing, research work, that's going to be successful. That is the idea in this one. So Cook has tried to prove that. So there is a famous theorem on this one, Cook's theorem. He has tried to prove that. He proved this one, that if satisfiability is lying in P, so it means where this P is we don't know. Even P can be in the intersection part of this one, right? So he said that satisfiability is in P if and only if P is equals to NP. Satisfiability will come into P if and only if P is equals to NP. Means satisfiability will become deterministic if P is equals to NP. He said that this PER can be proved as correct if you prove that satisfiability is in P. He did not prove it. He said that somebody proves this one, then our work is correct. Our work is perfect. So this is all the discussion behind NP hard and NP complete problems. So that's all about this one. So I may be making one more video for solving some NP hard graph problems, right? So leave a comment for this video. Let me know how much you have understood.